Today, we are going to talk about the test of differences between means. We will discuss the difference between the test between independent means and the t-test between non-independent or correlated means. We are going to apply the steps in hypothesis testing using z-test and t-test for independent means and also for dependent means or correlated means. This we will do with manual calculation using formulas and also with the SPSS software. To start, let's get to know the null hypothesis, which suggests that there is no difference between means. It has become conventional in statistical analysis to set out testing the null hypothesis, which says that two samples have been drawn from equivalent populations. According to the null hypothesis, any observed difference between samples is regarded as a chance occurrence resulting from sampling error alone. Therefore, an obtained difference between two sample means does not represent a true difference between their population means. In the present context, the null hypothesis can be symbolized as U sub 1 is equal to U sub 2, where U sub 1 is the mean of the first population and U sub 2 is the mean of the second population. Now let's take a look at some examples of how the null hypothesis is being stated. First, the Germans are no more or less obedient to authority than Americans. Another one, Protestants have the same suicide rates as Catholics. And one more, political conservatives and liberals discipline their children to the same extent. As you can see, here are these keywords, no more or less, the same. So it just means that the two means are denoted to be the same or equal. It should be noted that the null hypothesis does not deny the possibility of obtaining difference between sample means. On the contrary, it seeks to explain such differences between sample means by attributing them to the operation of sampling error. To conclude that sampling error is responsible for our obtained difference between sample means is to retain the null hypothesis. The use of the term retain does not imply that we have proved the population means are equal, or U sub 1 equals U sub 2, or even that we believe it. Technically, we are merely unable to reject the null hypothesis due to lack of contradictory evidence. Now let's talk about the research hypothesis, which suggests that there is a difference between means. The null hypothesis is generally, although not necessarily, set up with the hope of nullifying it. This makes sense, for most social researchers seek to establish relationships between variables. That is, they are often more interested in finding differences than in determining that differences do not exist. Differences between groups, whether expected on theoretical or empirical grounds, often provide the rationale for research. If we reject the null hypothesis, if we find our hypothesis of no difference between means probably does not hold, we automatically accept the research hypothesis that is a true population difference does exist. This is often the hoped-for result in social research. The research hypothesis says that the two samples have been taken from populations having different means. It says that the obtained difference between sample means is too large to be accounted for by sampling error. The research hypothesis for mean differences is symbolized. U sub 1 does not equal to U sub 2, where U sub 1 is the mean of the first population and U sub 2 is the mean of the second population. Let's take a look at the examples of how the research hypothesis is being stated. First, Germans differ from Americans with respect to obedience to authority. Another one, Protestants do not have the same suicide rates as Catholics. And last one, political liberals differ from political conservatives with respect to permissive child-rearing methods. If you can see, here are these keywords differ, do not have the same, and differ, which just implies that the research hypothesis is saying that the two means are different. Take note that the symbol not equal is read as does not equal. There we go. So here, if we accept the research hypothesis, it just means that we reject the null hypothesis. Now let's take a look at some important terms that is related to testing the difference between means. The first one is the sampling error, which is denoted as E of I. It is a difference between a population value or parameter and a particular sample value. Thus, if U is the population value of the mean and Xi is an estimate based on a random sample of size n, then the difference U minus Xi equals EI, where E of I is sampling error. Note that sampling error also refers to the chance variations that occurs in sampling. And it is also the difference that inevitably results from the process of sampling from a given population. The next one is standard error. It is the standard deviation of the theoretical sampling distribution. It is a standard deviation which describes the variability of a statistic over repeated sampling. It is descriptive of the variation of a statistic in a complete population of sample values. The standard deviation of the theoretical sampling distribution of the mean is represented by the symbol sigma naught. In practice, the standard deviation must be estimated from sample data. These estimates in the case of the mean may be represented by the symbol S of naught. The next term is independent samples. These are samples where the members of one group is chosen independently of the members of the other group. The sizes of the group compared need not be the same. Some examples are male administrators versus female administrators, and working student versus non-working students. Another term is correlated samples. These are also called dependent, paired, or matched samples. When samples are correlated, each individual in one group corresponds or is matched with an individual in another group. The sizes are the same. Examples are pre-test and post-test, husbands and wives, and all other matched pairs. The last term is t-ratio. This is the result of a t-test, a statistical technique that indicates the direction and degree that a sample means difference falls from 0 on a scale of a standard error units. Now let's go to Z and T tests. The Z test is based on the Z distribution, which is normal, as mean is equal to 0 and standard deviation equal to 1. The distribution of T was developed originally in 1908 by William Gossett, who wrote under the pen name student. The T distribution is frequently referred to as student's distribution. The T distribution is a family of distributions for various degrees of freedom. The number of degrees of freedom is the number of values of the variable that are free to vary given the restrictions on the data. Both the Z and T tests are used to test the significance of the difference between means. The formulas for computing these two tests are very similar, differing only in the determination of the standard error terms in their denominators. If the standard deviation of the population is known, the standard error term can be computed directly and the Z-test is in order. If the standard error is estimated from sample data, The appropriate test is the t-test. Now here are the statistical tests of significance and their appropriate use. We have the z-test, and this is used when testing null hypothesis of no difference between population means or large samples with n is greater than 30. T-test is used when size of samples compared is less than 30. Now we have two types of t-test. T-test for independent samples. It is used when scores of two groups are independent, that is, when groups to be compared are selected randomly from two different populations. Another one is t-test for correlated samples. It is used when matched groups are used and compared. Now we have a one-tailed test. It is used when it is certain that the mean score of one group is greater or smaller than that of the other. It is used for directional hypothesis. While two-tailed test is used when it is not known that the mean of one group is greater than or less than that of the other group. It is used for non-directional hypothesis. Now let's take a look at the requirements for testing the difference between means. First, you need a comparison between two means. And then, you need an interval data. And also a random sampling. And you also need equal variances. And lastly, a normal distribution. Here are the critical values for the z-test. For two-tailed test, we have an alpha of 0.05 and a critical region or z-value of 1.96. If the alpha is 0.01, the critical region or z-value is at 2.58. For one-tailed tests, the alpha level is 0.05 and the critical region or z-value is at 1.64. And if the alpha level is at 0.01, the critical region or z-value is at 2.33. Now for social sciences, we usually use an alpha level of 0.05 and with a z-value of 1.96. Yes, that's for social sciences. Now let's go over the formulas for z and t tests for two samples. First, you have to identify if the variance is known. If the variance is known, we use this formula. And then, if not, if the variance is not known, we have to know if the sample size is greater than or equal to 30. If both samples from the two means are greater than or equal to 30, we use the same formula. But if they are not equal or greater than 30, you have to know if the samples are correlated or paired or matched. Then if they are matched, we use this formula. If they are not, we use this formula instead. So we use these three formulas in finding the mean differences between two samples. Okay, if the variance is not known, we use this formula. So here below in the denominator, you'll find the df or the degrees of freedom. It is found by adding the two ends or the size of the samples and then subtract 2 from it, and you get the degrees of freedom. Then for the hypothesis, we have this use of 1 is equal to use of 2, or the population means are equal. That's our null hypothesis. And for the alternative hypothesis or research hypothesis, use of 1 does not equal to use of 2, or population means are not equal, or this is used for non-directional. But If there's a direction, use of 1 is greater than use of 2. You use the symbol greater than when population mean 1 is greater than population mean 2. And use of 1 less than use of 2 when population mean 1 is less than population mean 2. Next, let's talk about the degrees of freedom. How do you find the degrees of freedom? As I've said, you just combine the two sample sizes and subtract 2 if it's a t-test for independent samples. And if it's for correlated samples, you just use n-1 or the sample size, subtract 1 from it, and then you get the degrees of freedom. Now let's look at some examples of hypothesis testing using the formulas that we talked about a while ago. For z-test, a random sample of 51 minority children attending integrated public school has a mean of 81 with standard deviation of 3. An independent sample of 101 minority children attending a segregated public school has a mean academic achievement score of 79.9 with standard deviation of 3. Assume that the population variances are homogeneous. Determine whether there is a significant difference in mean academic achievement for these samples compared to a null hypothesis of no such population differences. Use of 1 is equal to use of 2. Let the level of significance be 0.05 and use a non-directional test. Now to solve this, we use the formula. But before that, let's find the null hypothesis and the research hypothesis. The null hypothesis is that there is no significant difference between the academic achievement mean of the integrated public school children and the academic achievement mean of the segregated public school children. And the research hypothesis then is there is a significant difference between the academic achievement mean of the integrated public school children and the academic achievement mean of the segregated public school children. Our alpha is at 0.05 and we use our z table at 0.05 and a two-tailed critical value of 1.96. And here is our solution. So for the first group of population of integrated public school children, we have n sub 1 as 51, use of 1 is 81, and standard deviation of 3. For group 2, our second population, segregated public school children, n sub 2 is 101, use of 2 is 79.9, and standard deviation 2 is 3. For our solution, we use the formula for finding the z-test value. Inputting the given values, we get this one. Z equals test value of 81 minus 79.9 over the square root of 3 squared over 51 plus 3 squared over 101. And we get a value of 2.11. So our decision rule is to reject the null hypothesis if the z value is greater than 1.96. So since 2.11 is greater than 1.96, our decision is to reject the null hypothesis in favor of our research hypothesis. It means that there is a significant difference between the academic achievement mean of the integrated public school children and the academic achievement mean of the segregated public school children. There you go. Now for the t-test for independent samples. Here is another problem. To compare two junior high schools A and B on academic effectiveness, an experiment was designed requiring the use of 15 sets of identical twins, each twin having just completed 6th grade. In each case, the twins in the same set had obtained their schooling in the same classroom at each level. One child was selected at random from each set and assigned to school A. The other was sent to school B. Near the end of the 9th grade, a certain achievement test was given to each child in the experiment. Test the hypothesis that the two schools are the same in academic achievement given the following results. So here are the results. We have in pairs A and B. We have 18 sample size. And to solve for this, we have the research question. Did junior high school A and B differ in academic effectiveness? Our null hypothesis is that there is no significant difference in the academic effectiveness between junior high school A and B, while our research hypothesis is that there is a significant difference in the academic effectiveness between junior high school A and B. Now we set our significance level at 0.05 and degrees of freedom is 28, and we use the two-tailed value, critical value of 2.048. How do we get 2.048? We look at the distribution table. So here is our alpha and our degrees of freedom, and that's how we find our critical value. For our solution, we just need to get the sums of the samples and then square the sums, square the samples. We get sample size 15 for A, 15 for B, then the sum of X, that's 1021 for A and 942 for B, and then we have the mean for A, we get 68.06, and for B 62.8, and then we have the sum of X squared, as A is 71.739 and B is 61,350. Okay, so we are going to use this formula to find our p-value. Note that the variance is not given, so this is the pooled estimate of variance. So first we need to find our variance using this formula. So we just substitute the values we found from our table, and then we get the value of 158.4. Now that we have our variance, we can now go back to our formula for t-test value, and we plug in the values that we found out a while ago, and we get the value of 1.14. So our decision rule is to reject h0 if t is greater than 2.048. But since the t value we got was 1.14, our decision is that we cannot reject the null hypothesis. That means that there is no significant difference in the academic effectiveness between junior high school A and B. So it's just basically the same, almost the same. Now let's go for another example, but now for t-test for correlated or dependent samples or can match pairs. Here's the problem. The attitude scores of 18 college students who went on a rural service program for 6 weeks are summarized below. So there we have the students, and then they have their scores before the rural service program and scores after the rural service program. And this D is the difference before minus after, and then B squared is the square of the difference. So we just get all the sums and we got D values. So the research question is that, is there a significant difference between the students' attitude before and after the rural service program? And the null hypothesis is there is no significant difference between the students' attitude before and after the rural service program, while the research hypothesis is that there is a significant difference between the students' attitude before and after the rural service program. We set our significance level at 0.05. The degrees of freedom is 18, or sample size minus 1, which is 17. And we get our critical value from our t-distribution table and find 2.110 here. Here's our t-distribution table. Our alpha is at 0.05 and our degrees of freedom is at 17, giving us a value of 2.1098. And when we round it up, we get 2.10. And to solve for this, we use our formula for t-test for dependent or correlated means. We just plug in the values and we get a t-value of 3.11. So our decision rule is to reject the null hypothesis if the t-value is greater than 2.110. So since our t-value that we found here is 3.11, our decision is to reject the null hypothesis in favor of the research hypothesis. That means that there is a significant difference between the students' attitude before and after the rural service program. Now let's go to independent samples t-test using SPSS Statistics. So here's our assumptions. We have 6 assumptions. First is that your dependent variable should be measured on a continuous scale. That is, it is measured at the interval or ratio level. Examples of variables that meet this criterion include revision time, which is measured in hours, intelligence, which is measured using IQ score, and exam performance, which is measured from 0 to 100, and weight, which is measured in kilograms, and so forth. Assumption 2, your independent variable should consist of 2 categorical independent groups. Example of independent variables that meet this criterion include gender, which are 2 groups, female and male, employment status, 2 groups also, employed or unemployed, and smoker, 2 groups, smoker or non-smoker, and so forth. Assumption 3 is that you should have independence of observations, which means that there is no relationship between the observations in each group or between the groups themselves. For example, there must be different participants in each group with no participant being in more than one group. This is more of a study design issue than something you can test for, but it is an important assumption of the independent t-test. If your study fails this assumption, you will need to use another statistical test instead of the independent t-test. For example, you can use a paired samples t-test. The next assumption is that there should be no significant outliers. Outliers are simply single data points within your data that did not follow the usual pattern. Example, in a study of 100 students' IQ scores where the mean score was 108 with only a small variation between students, one student had a score of 156, which is very unusual, and may even put her in the top 1% of IQ scores globally. The problem with outliers is that they can have a negative effect on the independent t-test, reducing the validity of your results. Fortunately, when using SPSS Statistics to run an independent t-test on your data, you can easily detect possible outliers. The next assumption is that your dependent variable should be approximately normally distributed for each group of the independent variable. We talked about the independent t-test only requiring approximately normal data because it is quite robust to violations of normality, meaning that this assumption can be a little violated and still provide valid results. You can test for normality using the Shapiro-Wilk test of normality, which is easily tested for using SPSS Statistics. And the last assumption is that there needs to be homogeneity of variances. You can test this assumption in SPSS Statistics using Levene's test for homogeneity of variances. Now you can check assumptions number 4, 5, and 6 using SPSS Statistics. Before doing this, you should make sure that your data meets assumptions number 1, 2, and 3, although you don't need SPSS Statistics to do this. When moving on assumptions 4, 5, and 6, we suggest testing them in this order because it represents an order where if a violation to the assumption is not correctable, you will no longer be able to use an independent t-test, although you may be able to run statistical tests on your data instead. Just remember that if you do not run the statistical tests on these assumptions correctly, the results you get when running an independent t-test might not be valid. Now, let's have an example of a problem of independent samples t-test using the SPSS Statistics. Here, a researcher studied the brains of smokers and non-smokers and wanted to find out if smoking has an effect on the size of the brain, particularly the frontal lobe of the participants of the study. Frontal brain volume measurements of 36 participants who were either smoker or non-smoker were collected. Our null hypothesis is that there is no significant difference in the size of the brain between smokers and non-smokers, and our alternative or research hypothesis is that there is a significant difference in the size of the brain between smokers and non-smokers. Open your SPSS data editor. In one column, input the frontal brain volume measurements, your dependent variable data, which are measured on interval ratio scale. And it goes from 7.3 all the way down to 3.7, a total of 36 participants in this sample. And then we've got our grouping variable. We have two groups, zeros and ones. Zeros are the non-smokers and ones are the smokers. Okay, and then how to label that? You can see it at variable view by clicking the tab at the bottom. Then to label the values, click this tab and input the data. Input 0 for value, then label it non-smokers, and then 1 for smokers. Then click OK, and then let's go back to our data view. Here is the dependent variable, the frontal brain volume. And then here is our independent variable, our groups of non-smokers and smokers. And then we click Analyze, then Compare Means, Independent Samples t-test, and there you go. We've got frontal brain volume here, our dependent variable, and then put that into the test variable window, then put group into the grouping variable box. Then we define the groups. Click Define Groups and put 0 for group 1, our non-smokers, and then 1 for group 2, our smokers. Then we click Continue. We can really use any number here like 1 and 2, 3 and 4, and so on. It doesn't matter. But 0 and 1 are probably what most people use in this case. And yeah. So we click OK, and then the output is produced by SPSS. Now this is the output viewer. Here we can see the actual results of our t-test. The first box here is the group statistics. In this box, we can see the frontal brain volume and the group of smokers and non-smokers. Sample size for non-smokers is 17 and 19 for smokers. We've got the mean of the frontal brain volume here too. Non-smokers have a mean of frontal brain volume of 5.3294, while non-smokers have a volume of 4.2947. And also we have our standard deviation for non-smokers and smokers. Non-smokers has 1.06170 and 0.946624 smokers. By looking at the means, you can obviously tell the difference equal to about 1, and the standard deviation is also equal to about 1. There. The next table that SPSS produces is the actual results of the t-test. Here you can see the Levene's test for homogeneity of variances. The independent samples t-test assumes that the variance expressed as standard deviation are the same in both samples. Now, they don't have to be exactly the same, but their values should be close enough to the extent that they are not statistically significantly different from each other, even though t-test for independent groups is relatively robust through violations of these assumptions, and you should still test them and report them in your results. So Levene's test of homogeneity of variances f is equal to 0.174, a very small f value, and the significance of this f is 0.679, which is not statistically significant. If you get a significant p-value of 0.05 or less, you would say that the variances are not the same in all probability. They are probably sampled from different populations, and so we become concerned about interpreting our t-value and our p-value if the homogeneity of variances assumption does not hold. But in this data, because the significance value is not 0.05 or less, in this Levene's homogeneity of variances test, we are confident that we can interpret the t-value and significance level associated with it. So here we have a t-value of 3.092 with a degrees of freedom of 34 and significance level of 0.004. So, because this value is less than 0.05, we would reject the null hypothesis between the means and state that, in our probability, that the difference in brain volumes between smokers and non-smokers is statistically significant. We should also note that SPSS also produces results for equal variances not assumed, in which it produces a t-value of 3.072 with degrees of freedom at 32.321 and the same significance level. So basically, the results are the same whether you look at the equal variances assumed or not, and that's because the variances are basically the same. The standard deviations are also very similar, and that's why the two t-values are very close to each other. SPSS also outputs the mean differences between the two means. There. The mean 5.32 minus the mean 4.29 gives us a mean difference of 1.03467. The standard error from these mean differences are also shown here, and then it gives us a confidence interval of the difference between the means. There you go. And that's our SPSS results. Let's go now to dependent t-test using SPSS Statistics. The dependent t-test, called the paired samples t-test in SPSS Statistics, compares the means between two related groups on the same continuous dependent variable. For example, you could use a dependent t-test to understand whether there was a difference in smokers' daily cigarette consumption before and after a 6-week hypnotherapy program. And your two related groups would be the cigarette consumption values before and after the hypnotherapy program. Now, let's look at the assumptions for dependent t-test using SPSS Statistics. The first assumption is that your dependent variable should be measured on a continuous scale. That is, it is measured at the interval or ratio level, just like the independent t-test. Examples of variables that meet this criterion include revision time, which is measured in hours, intelligence, exam performance, weight, and so forth. Another assumption is that your independent variable should consist of two categorical or related groups or matched pairs. Related groups indicates that the same subjects are present in both groups. The reason that it is possible to have the same subjects in each group is because each subject has been measured on two occasions on the same dependent variable. For example, you might have measured 10 individuals' performance in a spelling test, the dependent variable, before and after they underwent a new form of computerized teaching method to improve spelling. You would like to know if the computer training improved their spelling performance. The first related group consists of the subjects at the beginning of the computerized spelling training, and the second related group consists of the same subjects, but now at the end of the computerized training. The dependent t-test can also be used to compare different subjects, but this does not happen very often. Next assumption is there should be no significant outliers in the differences between the two related groups, just like the same with independent t-test. Outliers are just the single data points within your data that do not follow the usual pattern. The last assumption would be the distribution of the differences in the dependent variable between the two related groups should be approximately normally distributed. We talked about the dependent t-test only requiring approximately normal data because it is quite robust to violations of normality, meaning that the assumption can be a little violated and still provide valid results. Same with independent t-test, you can also test for normality using the Shapiro test of normality, which is easily tested for using the SPSS Statistics. Now you can check the assumptions 3 and 4 using SPSS Statistics. Before doing this, you should make sure that your data meets assumptions 1 and 2, although you don't need SPSS Statistics to do this. When moving on to assumptions 3 and 4, we suggest testing them in this order because it represents an order where if a violation to the assumption is not correctable, you will no longer be able to use a dependent t-test, although you may be able to run another statistical test on your data instead. Just remember that if you do not run the statistical tests on these assumptions correctly, the results you get when running a dependent t-test might not be valid. Okay, now let's take a look at an example of how SPSS Statistics is used in solving for the t-test for correlated means. Here's the problem. Researchers want to test a new anti-hunger weight loss pill. They have 10 people rate their hunger both before and after taking the pill. The null hypothesis is that there is no significant difference in the level of hunger before and after taking the anti-hunger weight loss pill. And the research hypothesis is that there is a significant difference in the level of hunger before and after taking the anti-hunger weight loss pill. Now let's look at the SPSS software, SPSS Statistics. Open your SPSS data editor. Right now we are on data view, which is where we input our data. Right now it is all blank. First, we need to tell SPSS what variables we have. So I'm gonna go down to the variable view. Here we have two variables, before the participants took the pill and after they took the pill. Now let's all leave this information as it is. Now that we have all our variables in here, we can now go back to the data view. The thing about SPSS is that every row represents a sample, or in this case, a participant of the study. Here we have 10 participants, each having a before and an after score. For example, person 1 has a before score of 9 and an after score of 7. Person 2 has 10, and then 6, 7, 5, 5, 4, 7, 4, 5, 6, 9, 7, 6, 5, 8, 5, 7, 7. There you go. Now we have our before and after scores of our participants. Now let's go to Analyze, then Compare Means, click on Paired Samples t-Test, and it's also the same as Dependent Samples t-Test or Matched Samples t-Test. Then we're led to a window like this. Here we click the before and after variable and put them into the paired variables window. Variable 1 is before and variable 2 is after. You can go to options if you want to specify the confidence interval. Right now we just leave it at 95% and we'll click OK, and the output is produced by the SPSS. The first table here shows the paired sample statistics, basically our mean, standard deviation, standard mean, error mean, and n. The mean of our before group is 7.3 and the mean of our after group is 5.6. Remember that these are ratings of hunger, so it seems to have go down here. Now let's look at the paired samples t-test to see if there's actually any difference. What we are most concerned here is our t-score, our degrees of freedom, and our significance level or p-value. So here t is equal to 3.597 with degrees of freedom of 9 and p-value of 0.006. Because the p-value 0.006 is less than 0.05, we are going to reject the null hypothesis and say that there is a difference between before and after. It means that the pill from our experiment could make a difference when it came to hunger. Now we're done with our lesson. What you've learned today: we apply the steps in hypothesis testing using Z and T tests, and we learned the difference between t-tests for independent samples and t-tests for correlated samples. We also learned how to solve for the Z and T tests manually using formulas and also by using the SPSS Statistics. Now that we have the idea how to test the difference between means, I hope that you will be using this in your researches. And that's all for today. Thank you very much.